Good day, everyone. We are the Group 7 who are asked to report Chapter 7, Runoff. I am Abigail A. Tapaya, who will report Slide 2 to 5. Lesson 1, Introduction. Runoff is nothing other than water running off the land surface. Just as the water you wash your car with runs off down the driveway as you work. The rain that Mother Nature covers the landscape with runs off downhill. 2. Due to gravity. Runoff is an important component of the natural water cycle. Oceans act as a large storehouse of water that evaporates to become atmospheric moisture. The oceans are kept full by precipitation and also by runoff and discharge from rivers and the ground. During a heavy rain, you might notice small rivulets of water flowing downhill. Water will flow along channels as it moves into larger creeks, streams, and rivers. Here's the picture of impervious areas cause excessive runoff. This picture gives a graphic example of how surface runoff, here flowing off a road, enters a small creek. The runoff, in this case, is flowing over bare soil and is depositing sediment into the river. The runoff entering this creek is beginning its journey back to the ocean. As with all aspects of the water cycle, the interaction between precipitation and surface runoff varies according to time and geography. Next picture is much of the water in rivers comes directly from rainfall runoff from the landscape. The small creek shown in the figure will merge with another creek, eventually flowing into a larger river. Thus, this creek is a tributary to a river somewhere downstream, and the water in that river will eventually flow into an ocean. The concept is not that much different from the small capillaries in your body carrying blood to larger arteries, eventually finding its way to your heart, analogous to the ocean. Here's the physical characteristics affecting runoff. Number 1, land use. Next, vegetation. Another, soil type. Drainage area, basin shape, elevation, topography, especially the slope of the land, drainage network patterns, and ponds, lakes, reservoirs, sinks, etc. in the basin, which prevent or delay runoff from continuing downstream. Human activities can affect runoff. As more and more people inhabit the earth, and as more development and urbanization occur, more of the natural landscape is replaced by impervious surfaces, such as roads, houses, parking lots, and buildings that reduce infiltration of water into the ground and accelerate runoff to ditches and streams. As a result, the peak discharge, volume, and frequency of floods increase in nearby streams. Here's the figure 3, where severe erosion can occur when people manipulate the landscape without regard to how flowing rainfall runoff will erode exposed soil.
Urban development and flooding. Urbanization can have a great effect on hydrologic processes such as surface runoff patterns. Imagine in this way. In a natural environment, think of the land in the watershed alongside a stream as a sponge, more precisely as layers of sponge of different porosities. Stream is looping uphill away from the stream. When it rains, some water is absorbed into the sponge and some runoffs the surface of the sponge into the stream. Assume a storm lasting 1 hour occurs and one half of the rainfall enters the stream and the rest is absorbed by the sponge. Gravity is still at play here, so the water in the sponge will start moving in a general downward direction. So next, imagine that roads and buildings have replaced most of the watershed surface. When rainfall occurs, it can infiltrate this impervious surface and will quickly run off directly into the stream. And it will result in a very quick and short-lived urban flood, rather than a gradual rise and fall into the river. So, a flood lasting even 10 short minutes is enough to ruin your basement. Next is lesson 2, quick flow and delayed flow. So, after a rainfall, the amount of water that flows into stream and rivers that cause the stream to rise above its stable condition. It's sometimes called storm flow, quick flow, or direct runoff. This flow of water occurs relatively quickly to channels and causes water levels to rise, peak, and then recede as the storm water drains from the watershed following the storm. Base flow, also called drought flow, groundwater recession flow, low water flow, low water discharge, and sustain, delayed flow and sustain, or runoff, or fair weather runoff. So, ang base flow is a portion of stream flow that is not directly generated from the excess rainfall during a storm event. Next is a hydrograph. A hydrograph is a graph or plot that shows the rate of water flow in relation to time given a specific point or cross-section. The rate of flow is typically expressed in cubic meters or cubic feet per second. It can also refer to a graph showing the volume of water reaching a particular outfall or location in a sewerage network.
Okay, so makikita po natin sa figure 4 yung rate of flow of storm or the storm hydrograph. And wherein makikita din natin dyan yung components of the hydrograph, which is the rising limb, the peak, and the falling limb. Nandyan din yung peak rainfall, the lag time or the difference between the peak rainfall and the peak discharged. Meron din storm runoff, the through flow, and the base flow or the antecedent. Nandyan din po yung height or the height at which the flood may occur, which is the bank full discharge. And also the discharge line or how much water is in the river. So next slide, the unit hydrograph. The unit hydrograph is a direct run of hydrograph resulting from 1 unit, 1 inch or 1 centimeter of constant intensity uniform rainfall occurring over the entire watershed. The concept of unit hydrograph is based on linear systems theory and follow the principles of superposition and proportionality. So for example, if 1 inch of excess rainfall produces a direct runoff peak of 100 CFS, then 2 inch of excess rainfall would produce a direct runoff of 2 times 100 is equals to 200 CFS. Similarly, if 1 inch of rainfall is followed by 2 inch of rainfall, the hydrographs from both rainfall pulses are simply added after accounting for the necessary time lag. The following figure demonstrates these concepts. So ayun nga, dito po sa figure 5, the unit hydrographs for different rainfall depths. So ayan po nakalagay na the blue is 0.5 inches or inch rather. The red one is 1 inch and the green one is 2 inches. So ayan po nakalabel na po dyan yung runoff over time po. So ayan po yung unit hydrograph. So let's come for the lesson 3, the sources and components of runoff. Considering a catchment area receiving precipitation, for a given precipitation, when the evapotranspiration, initial loss, infiltration, and detention storage requirements are satisfied, the excess precipitation moves over the land surfaces to reach smaller channels. This portion of runoff is called overland flow and involves building up of storage over the surface and draining of the same. So, ang tawag po dun is overland flow and nagbibuild po siya ng storage over the surface and draining of the same. Next, the flow is in this mode where it travels all the time over the surface as overland flow and through the channels as open channel flow and reaches the catchment outlet is called surface runoff. So, pag nag-travel na daw po yung flow na nasa mode na overland flow, nag-travel na po siya through the channels as open channel flow, tapos nakarating na po siya sa catchment outlet. So, tinatawag na po siyang surface runoff. Next, a part of the precipitation that infilters moves laterally through upper crusts of the soil and returns to the surface at some locations away from the point of entry into the soil. This component of runoff is known variously as interflow, throughflow, storm seepage, subsurface flow, or quick return flow. So, ayan po yung component ng runoff. Ayan po, component of runoff.
Next, types of runoff. Number 1, surface runoff. It is the amount of water which is drained over the surface of the soil of watershed after saturation of micro and micropores of soil and under gravitational pull from a higher altitudes to lower altitude having a much defined rate of flow. Next, number 2, subsurface runoff. When surface storage of soil in the watershed is completed and it becomes saturated, water begins to flow in the surface of soil up to the depth of 1 meter from a higher altitude to lower altitude at the rate much less than surface runoff. It takes hours and even days to reach the stream. It is clear water and maintains the stream flowing after precipitation. Next slide. Factors affecting runoff. The main factors affecting the runoff from a catchment area are: number 1, precipitation characteristics. Precipitation is the most important factor which affects runoff. The important characteristics of precipitation are duration, intensity, and areal distribution. Next, duration. Duration is total runoff depends on the duration of rainstorm. For a given rainfall intensity and other conditions, a longer duration rainfall event will result in more runoff. Next, intensity. Intensity is the rainfall intensity influences both rate and volume of runoff. The runoff volume and also runoff rate will be greater for an intense rainfall event than for less intense event. Next, areal distribution. Areal distribution is it also influences both the rate and volume of runoff. Generally, the maximum rate and volume of runoff occurs when the entire watershed contributes.
Shape and size of catchment. The runoff from a catchment depends upon the size, shape, and location of the catchment. The following are the general observations. First, more intense rainfall events are generally distributed over a relatively smaller area. Larger the area, lower will be the intensity of rainfall. Next, the peak normally decreases as the area of the basins increase. C. Larger basins give a more constant minimum flow than smaller ones. Letter D. The fan-shaped catchments give greater runoff because these tributaries are nearly of the same size and hence time of concentration of runoff is nearly same. On the contrary, discharges over fern leaf arrangement of these tributaries are distributed over the period because of the different lengths of tributaries.
Number 3. Topography. The runoff depends upon surface condition, slope, and land features. Runoff will be more from a smooth surface than from rugged surface. Also, if the surface slope is steep, water will flow quickly and adsorption and evaporation losses will be less, resulting in greater runoff. On the other hand, if the catchment is mountainous, the rainfall intensity will be high and hence runoff will be more. Number 4. Geology characteristics. Geology characteristics include surface and subsurface soil type, rocks and their permeability. Geology characteristics influence infiltration and percolation rates. The runoff will be more for low infiltration capacity soil or clay than for high infiltration capacity soil or sand. Fifth, meteorological characteristics. Temperature, wind speed, and humidity are the major meteorological factors which affect runoff. Temperature, wind speed, and humidity affect evaporation and transpiration rates. Thus, soil moisture regime and infiltration rate, and finally runoff volume. Sixth, storage characteristics of a catchment. Presence of artificial storage such as dams, weirs, etc., and natural storage such as lakes and ponds, etc., tend to reduce the peak flow. These structures also give rise to greater evaporation. Next is sources and components of runoff. First is channel precipitation. Precipitation that directly falls on open water bodies such as rivers, lakes, ponds, etc. An important component of runoff only under these conditions. Two conditions. A is arid regions where most rainfall over land is adsorbed. B is the areal fraction of open water bodies is relatively large. Number 2. Overland flow. Water that flows over the ground surface to stream channels. It occurs sometimes as quasi-laminar sheet flow, but more often as an anastomosis, or network of trickles and rivulets. Number 3. Through flow. Water that infiltrates the soil surface and then moves laterally towards the stream channels in the upper soil horizons. It moves either in the unsaturated zone or slow, or the perch saturated zone above the main groundwater. It is also called subsurface zone above the main groundwater. It is also called subsurface storm flow, storm seepage, and secondary base flow. Conditions where true flow occur include: A. Thin permeable soil overlies impermeable bedrock. B. The soil layers are distinct. C. There exists an iron pan or bluff pan. Number 4. Groundwater flow. Water that infiltrates the soil surface and then percolates to the underlying groundwater will move laterally to mainstream channels through significant in the quick flow through the piston mechanism.
Another source and component of runoff is through flow. Water that infiltrates the soil surface and then moves laterally towards the stream channels in the upper soil horizons. It moves either in the unsaturated zone or the perch saturated zone above the main groundwater. It is also called subsurface zone above the main groundwater. It is also again called subsurface storm flow, storm seepage, and secondary base flow. There are conditions where through flow occur. This includes thin permeable soil overlies impermeable bedrock. Second, the soil layers are distinct. Third, there exists an iron pan or plow pan. Fourth source and component of runoff, the groundwater flow. Water that infiltrates the soil surface and then percolates to the underlying groundwater will move laterally to mainstream channels through the saturated zone. It contributes mainly to the base flow, but can also be significant in the quick flow through the piston mechanism. In this slide, the 22nd slide, we can see in the figure 6 the components of runoff, and in the figure 7 the diagrammatic representation of the runoff process. So let's proceed to lesson 4. Lesson 4: the effects of surface runoff. After a rainstorm, you have probably noticed water running over large flat surfaces such as parking lots, roofs, driveways, sidewalks, farm fields, roads, and lawns. This surface water runoff is known as storm water. As we replace forests and fields with hard impervious surfaces, more rain runs off the land instead of soaking into the soil. This increases the amount of stormwater runoff, which has been identified as the leading contributor to water quality pollution in the Puget Sound. Pollutants carried by stormwater such as heavy metals, petroleums, products, excess nutrients, and pathogens have harmed many creeks, lakes, rivers, bays in all parts of the world. There are some other effects from stormwater runoff. To be exact, proper damage, water pollution, beach and shellfish closures, increased algal growth in clouded water.
So for our lesson 5, the runoff from snow. Covered areas, if you live in Florida or on the French Riviera, you might not wake up every day wondering how melting snow contributes to the water cycle. But in the worldwide scheme of the water cycle, runoff from snow melt is a major component of the global movement of water. Of course, the importance of snow melt varies greatly geographically, and in warmer climates, it does not directly play a part in water availability. In the cooler climates, though, much of the springtime runoff and stream flow in rivers is attributable to melting snow and ice. So, also, mountain snow fields act as natural reservoir for many western United States water supply systems, storing precipitation from the cool season, when most precipitation falls and forms snowpacks, until the warm season, when most or all snowpacks melt and release water into rivers. As much as 75% of water supplies in the western states are derived from snowmelt. So 75% or mas marami pa or kasing dami ng 75% ng water supplies sa western states are derived from snowmelt. So, paano daw nagko-contribute yung snowmelt sa stream flow? So, a good way to visualize the contribution of snowmelt to stream flow in rivers is to look at the hydrograph below. So, dito po sa figure 8, the hydrograph for snowmelt, dito po nakalagay yung contribution of snowmelt sa stream flow. Note that runoff from snowmelt varies not only by season but also by year. So, ayan po, nakalagay po dyan yung kung gaano kataas yung runoff sa snowmelt through the varies nga sa season tapos sa year. So this shows daily mean stream flow or the average stream flow for each day for 4 years for the North Fork American River at North Fork Dam in California. The large peaks in the chart are mainly the result of melting snow. Although storms can contribute runoff also, compare the fact that minimum mean daily stream flow during March of 2000 was 1,200 cubic feet per second, while during August, stream flows ranged from 55 to 75 cubic feet per second. So next, let's come from the snowmelt and flooding. The effects of snowmelt on potential flooding, mainly during the spring, is something that causes concern for many people around the world. Besides flooding, rapid snowmelt can trigger landslides and debris flows. So nati-trigger or nagkakaroon ng landslide or mga pagguho ng mga debris, epekto siya ng rapid snowmelt. Effect from rapid snowmelt rather. In alpine regions like Switzerland, snowmelt is a major component of runoff. So, major component daw ng runoff yung snowmelt sa mga alpine regions like Switzerland. So, in combination with specific weather conditions such as excessive rainfall on melting snow, for example, it may even be a major cause of floods. So, yung excessive daw rainfall, like excessive rainfall from melting snow can also cause major cause of floods. So, in Switzerland, snowmelt forecasting is being used as a flood warning tool to predict snowmelt runoff and potential flooding. So, ginagamit daw yung snowmelt para matukoy yung mga kung may flood na papadating. So, magsisilbi siyang warning tool para ma-predict yung snowmelt runoff and potential flooding sa isang lugar or state. Like for example nga sa Switzerland. So, that's all for our reporting. Thank you.